Well, welcome everyone. I really appreciate everyone showing up and coming to this. Probably this will be the last webinar, 10-4CT webinar of the summer. We're not going to continue for July and August. We need a rest. You guys need a rest. So we'll resume in September. But I'm really pleased to welcome Aaron Miller from SHARC Energy to speak with us today. Jess Silver-Byrne from Building Decarbonization Coalition introduced me to Aaron a couple of months ago. And I was really glad to make the connection partly because as much as I'm interested in sewer thermal energy and wastewater thermal energy, I still tend to think of thermal energy networks as being a function of uh, drilling boreholes. How many are there going to be, and how deep are they going to be, and where you're going to put them? And it, even though I know it leaves out this whole realm of where to grab thermal energy and make use of it. So with that, I'm going to turn things over to Aaron Miller, who can uh, give you a much better introduction about who he is and his experience than I can. But I'm really glad to have you, Aaron, and I'm going to turn things over to you now.
Thank you. Appreciate the invitation and that very warm welcome. I'm Aaron Miller. I'm with SHARC Energy. I'm based in New York, but I basically handle the entire eastern half of the continent, and that line keeps drifting west. So I'm building projects of all scales and sizes across the continent. And actually, we've got projects working in Europe and Australia as well. So really happy to be here. And let me jump right into it. I'm going to start with some technical background, right? Just to set the stage. I don't want to bore you guys with tons of slide deck. If you want to do a really deep dive, no pun intended, into wastewater energy transfer and how the tech works, happy to do it offline. I just want to kind of get through what the boxes that we offer, we're a manufacturer, what they do to demonstrate really to get to the meat of the conversation, which is like, here's some projects that are in the field working, and here's how we could potentially deploy these or bring these to Connecticut. So just to set the stage, why wastewater? There's so much untapped energy. It really is the last and the largest renewable resource we have available. To give you some context, 1 million gallons of wastewater a day, right? So you think about a small lift station or pump station in your town handles probably about 3 to 5 million gallons a day. Not surprising. It sounds like a lot, but it's not really. When you think about all the sewers and the toilets and the showers. And so every million gallons that runs through that plant is a possible megawatt of energy you can harvest. So 1 million gallons a day equals 1 megawatt of energy. Think about that. So New York City DEP, just down the road from where I'm at, they handle 1.3 billion gallons a day. That's 1,300 megawatts of energy that are being flushed down the toilet every day. Think about what you could do with that energy if we could just harvest it, capture it for a few minutes, harvest the energy, and then send it along its way. So one of the reasons why wastewater is such a rich, valuable energy source, in addition to its abundance, is the consistency of its temperature. So here's some temperature from data from Toronto. You can see that the red line, which is the outside temperature, dead of winter versus peak of summer, big swings in temperature. And there you can see the orange and blue line, which is really that's the geothermal loop. It trails the ambient temperature by just a month or so, right? So you have those swings in the geo loop. So you have to get into balancing and making sure you're not taking too much energy out or putting too much in during certain times of the year. Whereas you look at that sewer temperature, 60 some odd degrees year round, super consistent temperature. So I've got constant flow and constant temp. That's a dream condition for heat pumps. You've got now a condenser water loop with just all year round just running energy. So now the question is, how do you harvest the energy out of that? Otherwise, the water that you wouldn't want to touch, right? We have two boxes, now three technically, and it all comes down to scale. Piranha and the SHARC, right? And I'm going to use multifamily residential as just the to kind of set the basis because it's our sweet spot and it's the easiest way to describe the technology because multifamily residential buildings have very, very predictable wastewater flows, right? This many people are going to make this many gallons of wastewater, and they have very predictable domestic hot water peaks, loads. Like usually you've got morning peaks, evening peaks as far as hot waterways, right? Take a shower in the morning, at night, You take a shower, you boil pasta, you bathe the kids, you do dishes. A lot more hot water waste in the evening, right? So what we're trying to do with our technology is capture enough of that wastewater during the day to account for those peaks to make sure that we can match the load that the building or the loop requires. And how we do it is with these two, now three boxes, as you'll see. We've expanded the SHARC deployment. But the reason why I'm sitting on this slide for a while is I want you to look at the white the market sectors in that white section, right? It's not just about multifamily residential. It's not just about sanitary water, right? Commercial laundries are great. Car washes. You can read these better than I can read, right? So anywhere there's hot hydronic waste heat, I'm working with a soy sauce manufacturer right now. I'm working with a milk producer, and they've got these huge, vats of essentially warm milk waste that we're just going to, instead of flushing it, we're just going to run it through our heat exchanger, extract some of that energy, and put that energy back into the milk plant to help them boil and make their cheese. So again, it's just that perfect circular economy, as you can see at the bottom here, repeatable, scalable, and circular. Because you can scale these machines up, and essentially, if you put one of these boxes in the basement of a multifamily residential building, and you give me access to all of the wastewater coming out of that building, we can make 91% of the hot water for that building. It's almost a perfect circular economy. So imagine, if you will, a heat pump. And I'm going to get through the Piranha quickly because we're here to talk about thermal energy networks, district systems. This is more useful at a building scale, but I just want you guys to know that it's available, that you can make hot water for a multifamily residential building or a commercial laundry or a bagel factory or a car wash or a hotel, right? Just by capturing the wastewater before it leaves the building and running it through the system. So what we have here, imagine if you will, inside this tank, this box, excuse me, is a big metal tank with like a waffle weave or a golf ball dimple pressed into it. Then we wrap that tank in another sheet of steel and insulate it. So now I've got a gap between these two plates of steel and I'm passing refrigerant between them. So what I do is I fill this tank up. What you don't see off slide is a battery. It's our tank, our wastewater holding tank. Because again, in either in a multifamily residential building or even in a outside sewer, gravity-fed sewer main, you're going to get those peak flows and those low flows. So we want to capture enough wastewater in a battery, a tank, so that we, just like solar, right? If you want to use solar power at night, you have to store it in a battery to use it off hours. Same thing here. We're trying to capture the wastewater in those peak hours so that we can run it during off-peak hours when A, demand is low, and B, when electricity is cheaper. So off camera or off slide, I have a tank with wastewater in it. I pump it into this tank, solids and all. 4-inch and 6-inch inlets and outlets. If you can flush it down a toilet, you can pass it through our system. Not a problem. Fill this tank up with all that wastewater. Heavy solids fall to the bottom. They get flushed out or pumped out multiple times a day, just like a toilet would. Any excess volume goes over the top. The trick is we're trying to fill this tank up with that 70 some odd degree water that comes out of a building year round. And then we're slowly extracting the energy out of that wastewater, right, into the refrigerant that's passing between it in that around that tank. Then we run that warmed refrigerant through a compressor. This is just standard heat pump 101. Refrigerant through a compressor into a brazed plate heat exchanger. What that means is it's designed for potable water, meaning that the refrigerant and the potable water are completely separated by an air gap. There's no cross contamination. So what we do is we run this refrigerant through this way through the compressor and run domestic cold fresh water in opposite flow. And the speed through which we run that cold water through this exchanger, that determines the set point. We can give you 140-degree Fahrenheit hot water all day, every day, out of the 70-degree water coming out of your building. But if you need 120 or 130 because you're trying to do a preheat play or COP, we just speed the water up and we just cool the water. It doesn't have as much time to heat up. So that's your set point. Really easy to maintain, retro commission, and set as you needed. And if your building happens to have a secondary loop in it, right? Like a condenser loop, or you have geothermal in your building and you've got that ground loop that's running between all the apartments, well, let me tap into it. And then what I can do is I can have the Piranha look at your sanitary water temperature and your geothermal loop temperature, or whatever that loop is we're connecting to it, and it will determine which energy source is richer and then toggle between those two to make sure that it maximizes the efficiency and the capacity of the hot water production. So imagine this is happening right now in a building in Brooklyn. They've got geothermal It's an all-electric building. In fact, I'll talk about it a little bit later, Alafia. They've got a geothermal loop providing condenser water to all the apartments in the building. Heat pumps are doing heating and cooling. And it also feeds our hot water heat pump. And then there's also a sanitary tank that's dug under the parking deck for the building. So when the Piranha turns on for hot water, it looks at two thermistors. It looks at the tank and the loop. Let's say the tank's at 68 degrees, but it's the middle of the winter time, and everybody in their apartments is taking energy out of that geo loop to heat their apartments. So that loop is really, really cold, right? 45 degrees. Well, we don't want to touch that. We don't want to get too close to freezing. So we'll just pull off the sanitary tank. Imagine now summertime flips the script. Your tank is still about 68, 70 degrees year round, but now your ground loop, your geothermal loop is like 95 degrees because every apartment is pushing heat into that loop. So when the Piranha turns on, it looks at 70 degrees and 95. It's like, oh, I'm going to pull off this. And then again, throughout the year, it just picks whichever one's richer. So again, it's a really, really cool off-script way to now make hot water using all electric principles. So this is Piranha. I wanted to see if anybody has any questions about the technology before I move on to our larger system, the SHARC. Um, I don't see the chat up. I'm trying to keep my window open. So do you see anything, Bernard or Peter?
I
Don't
don't.
see anything,
Great.
um, but I did want to, so the Piranha, this
Yes.
is really focused on domestic hot water. Is that,
So it's potable hot water. So yes, that's its main play, and just but again, here's a perfect example, a great lead question for Bernard, actually. So yes, although potable hot water for domestic heating is really what its main play is, you can use it for processed water. Like I said, I'm using it at a bagel factory. I'm looking at it at a car parts manufacturer where they need hot water to wash down the vats that they're tumbling these things in, right? This slide I've made for K through 12 schools in Maryland because every school put geothermal in under the soccer field because it was so heavily incentivized. The problem is schools are very cooling dominant in Maryland and very seasonal. So these geoloops were getting super saturated with heat and useless essentially. So what we're proposing is put a Piranha in, attach it to the ground loop, take some of that excess heat out of the ground loop to make hot water for the school, thereby bringing the temperature of the ground loop down so that all the other water-based assets on that loop, right, can operate in full capacity and efficiency. Flip the script in Minnesota, we're doing the same thing for schools that are stripping geofields. So what we're proposing is use sanitary from the school, make hot water and shove it into the ground loop. Don't use it for your school right now directly. Shove it into the ground loop to bring that loop up to temperature so that all the other water-based assets, again, are connected to that loop, are operating at capacity and efficiency. And then once that loop tempers and hits the right temperature, a three-way valve switches, and then you store the rest of that hot water for the school. And the system just toggles between tempering the ground loop, making hot water for the school. So again, there's an application where we're using potable water for a non-potable application. So just my boss likes to say, don't think outside the box, pretend like there is no box. You know,
well,
Aaron, so Catherine
please,
Deviney from West Hartford has a question in the chat. Are there
please.
any code, building, or health issues, meaning code issues, with this in Connecticut or in other states? And sort of related to this, I was talking about
mhm.
um, sewer thermal energy, wastewater thermal energy to somebody, and they were really concerned about cross-contamination. Could you address that
Sure.
issue plus code issues?
Sure. So I kind of blew through this because I didn't want to just sit here and read to you, but we use an NSF 372 rated brazed plate heat exchanger. What that means is, again, the sanitary stays completely separated from the refrigerant, and the refrigerant and the sanitary both stay completely separated from the potable hot water. And if there is any leaks, it'll all go to environment. There will never be any cross contamination. Happy to do again. If the city, if you're municipal, if the codes department wants to dive into this, I will say this. My technical director, Brock Turnbull, and I went in front of the Massachusetts Plumbing Board a couple years ago to kiss the ring, and we got the blessing because in the state of Massachusetts is the toughest with regard to, excuse me, the Commonwealth. Massachusetts is the toughest when it comes to um, potable hot water. So we've got the blessing in Massachusetts. That's the one state that really gave us a hard time. The other one, believe it or not, was Minnesota. But and it's only because of a single word in the code. We're working through it with them. And to full disclosure, we're now working through a couple of acronym names, APMO and the other firms out there to get this into the universal plumbing and mechanical code. So no, you should have no concerns. We have dozens of these systems operating all across Canada and the United States. So no safety concerns whatsoever. And it's completely sealed. So you can operate this and our Shark inside of a building envelope without any odor. So again, the system, as long as it's designed properly, right, with normal plumbing ventilation like you would have in a standard building, there should be no problem whatsoever. Um, I hope that answers your question. And again, happy to do a deeper dive with you if you'd like to offline, and I'm happy to talk to your codes and compliance folks as well.
Great. I think that takes care of it. Yeah, so feel free to go on.
Sure. Okay. Well, whereas the Piranha really is a one-way street, waste heat in, potable hot water out, the Shark is our larger system, our namesake, is a passive filtration system. The easiest way to think about this is geothermal, but instead of using groundwater, we're using alternative water sources. Black water, the nasties of the nasties, gray water, data center, chilling. It doesn't matter. As long if you've got a water stream, even with solids in it, um, that we can run through our system and properly filter out enough of those solids, we can use that wastewater stream as a heating source or a heating sink. One of the things that, again, this is one of the misnomers when people say heat recovery, they only think about taking energy out of the sewer. With these passive house design buildings and a lot of these net zero ready situations, and especially now with data centers needing cooling at massive capacity, the heat rejection is going to be key, where we're going to be able to reject heat from a cooling loop into another loop as opposed to evaporating it to atmosphere. The other thing, the difference is we're talking about scale here. The Piranha, low and slow, right? We're making hot water over like a 16 to 18 hour period. Here with the Shark, we're dealing, as you can see, with, a minimum of 100 gallons per minute. I'll explain in a minute why. But we're dealing with each machine. The baby Shark can handle 550 gallons of raw sewage a minute. Our big system, the 880, as you can see, can handle 1,200, and we can stack these side by side. For instance, I'll talk to you in a bit about this project out in Vancouver, where we have five of our 880s side by side, filtering 6,000 gallons of raw sewage every minute to provide hot water for 23 million square feet of indoor space in Vancouver, right? So we've got that kind of scale down to a 35 unit apartment building in Boulder, Colorado. The key with Shark is we're using kWh of electricity to move some small pumps and motors, but you're getting megawatts of thermal transfer on the back end. That's the trade-off. It really is almost an exponential input to output ratio. You're only limited by the heat pumps that are connected to the clean side of our heat exchanger that are actually doing the work. What the Shark is doing is it's taking the wastewater and putting it, filtering enough of it to make it into a state that you can use it essentially to power a heat pump. That's really all we're doing here, right? Instead of pulling water out of the ground, for instance, we're taking water from your sanitary line of your building or from the sewer in front of your street, and we're using that water just like we would in geothermal. And again, because of that passive filtration, either way, forwards or backwards, we can do, as you can read here faster than I can read it to you, domestic hot water production, heating, cooling, and the really exciting stuff is the geothermal loop offset and conditioning, especially for these district systems. And again, as I mentioned with the Piranha, it's completely sealed. So you can be literally filtering thousands of gallons of raw sewage inside of your building and you won't know it because it has no odor. It operates below 70 dB, so you can have a conversation right next to it, and surprisingly small footprint. In what amounts to about 3 car spaces, you can convert 1.5 megawatts of thermal energy. Think about that, right? That's it's pretty impressive bang for the buck. This is what the Shark looks like. We typically like to have it in a linear fashion, easier for service and just for connections. But I like to show this picture because it lets you show that the Lego set can be kind of put together for the most part with a lot of flexibility in how you do it. Um, Real quick, again, not to bore you, we've got a heat exchanger that we're trying to do like heat source, heat sink, and I've got a wastewater stream with some solids in it. So what we've designed is a very specialized front end which filters out those solids and a wide gap plate and frame or a shell and tube heat exchanger, depending on what you need, because we're very Canadian in that regard, very flexible. We're not only wastewater agnostic, but we're also heat exchanger agnostic. If your municipality, let's say Hartford, really the guy or gal who runs the wastewater treatment plant really likes shell and tube heat exchangers, no problem. We will get to that. We don't need to force you with the plate and frame, even though it's smaller or less expensive. But regardless, there's a comfort factor, especially with these larger district systems. So the tank that I was mentioning before for the Piranha acts as a battery. Same thing here with Shark. But because Shark is we're concerned about solids, where Piranha we don't really care, we just pass it through. The tank also operates as a way for us to separate some of those large solids out. So the tank, the battery now has a large volume of water with heavy solids at the bottom, right? Fats, oil, and greases at the top, and we stage our pump in the middle so that we're pulling from that column of cleaner water. But even with that proper design, some stuff's going to get through. So that's why we have a macerator on the front end, the very first step. Imagine one of those dumpsters that eats cars, but vertically oriented, very low speed, high torque scissor stacks that are cutting big pieces into small pieces. So anything that does make it through our primary screening gets cut up here and pumped into the Shark. And this is what you saw on the previous slide. This motor rotates an auger with some stiff bristle brushes. They rotate, push those large solids down and out. And the bottom, there's a solids handling load pump, pulls all those solids out with about 10% of the wastewater. And then this basket filter has very small perforations. So anything, excuse me, as the brushes are rotating, pushing those solids out, anything that makes it through those holes is now no larger than about 2.5 millimeters in size. So a very small grit, if you will. So now I've got this sludge with suspended solids goes into this piping and valving section, and it auto reverses like a pool once an hour for about 2 minutes just to keep things clean. Because in this plate and frame heat exchanger, the plates have little teeth and grooves on them to increase surface area, but that allows things like fibers and hairs and what other things to get caught on them. So by reversing the flow once an hour, we knock them loose and we can pull them out. So again, we're cleaning the system while we're operating it. And now here, I mentioned before, 100 gallons a minute is my minimum, because the trick is this. I've got a plate and frame heat exchanger with 8 millimeter gaps, and I've got suspended solids about 2.5 millimeters in the water. So by keeping that scrubbing velocity up, keeping that flow up, I can move that sludge through this heat exchanger, do my thermal transfer without any of the stuff dropping out. And knock wood, in 16 plus years, we've never once had to open one of these bad boys up when it's been operated properly. So I want to get to some projects. So real quick, just wanted to show you, here's the Shark and heating mode, right? Here's that tank I was talking about. We're pulling the wastewater out of the tank. Here's your macerator. Heavy solids drop back out. They go back to the tank or right to city sewer to pull them out. In this operation, we're taking heat from the wastewater, mixing it into the building process loop vis-a-vis the heat exchanger. I've reversed the flow of the Shark, and now I can take rejected heat from your chiller plant, right? Instead of sending up to a cooling tower, send it down to the Shark, and I can take the heat out of that chilling loop, mix it into the sanitary, and flush it down the toilet. So heat source, heat sink, just like geothermal. And when you're fully leveraging the Shark's value prop, and this is where we get into the district, is when you're using sanitary to support an ambient loop, right? So now instead of moving hot water around, I'm moving 60 to 80 degree, 66 to 80 F degree water around, and I can have heat pumps connected to that same loop doing simultaneous heating, cooling, and hot water production. And the more heat pumps you put on that loop doing different loads and sharing that ambient water, the loop becomes really self-sufficient. And now we're just using the sanitary water, the Shark, or the geothermal loop. Again, think of it that way, to just keep that loop trimmed in that ideal range so that these heat pumps are maximizing the efficiency and capacity. It's really the same gig. And about geothermal, if any of you have explored it or looking into it or interested, this slide describes about 60 to 70% of the new construction and retrofit work that I'm doing in the Northeast, where they're using geothermal, especially in states like Massachusetts and New York, where it's so heavily incentivized to electrify existing or new building stock. So what's really cool is, all right, you've got these buildings connected to an ambient loop. we did a study and it's now operational for a building in Brooklyn. Again, the same one of the same buildings I was describing before. When they did the initial analysis, they said, okay, all electric, no gas building. We're going to need 128 boreholes at 500 feet to cover the whole thermal load of the building. Great. Let's drop SHARC into the energy model and do some heat recovery. Surprise, because of the passive house design of the building, it's the building envelope is so tight, it doesn't need a lot of heat. It needs cooling. It's a very cooling dominant building. So by putting the SHARC into the energy model and using it to pick up the peak cooling loads of those 5 or 6 really hot days, they were able to right size the bore field to pick up just the base cooling load of the building. Think about that. So they were able to go from 128 boreholes down to 90 because that additional capacity was being picked up by the sanitary, the SHARC. So there's real CapEx savings opportunities here where you can potentially short loop your geo loop. As Pete was mentioning before, how many holes do you need? Well, when you're spending 55 to 65, maybe even more $1,000 per hole, and I can reduce the number of holes you need by 20, 30, sometimes even 40%, that's a huge first cost savings, right? And now using the sanitary over the lifetime of the loop to keep that loop trimmed in that 66 to 80 degree Fahrenheit range, you'll get the operational savings, the OpEx savings over the 20 to 25 years. So it's one of the reasons why our system is so tailor-made for energy as a service or that ESCO model where there's performance contracting over a long period of time and you kind of, the owner operator essentially acts as a utility to the people who are, living in the building or in the campus. These types of systems really pay off because of that CapEx, OpEx savings model. And the other thing I also want to show here is just that, not to be glib, but I don't care what the nature of your wastewater is, right? As long as it doesn't corrode stainless steel, we're okay. And then I really don't care where you want to put the energy, as long as you have some place for me to put it. And these are all actionable items that we're doing right now, right? I'm using wastewater from a building to help preheat aqua for the hydroponics for a cannabis plant. Like Jen, snow melt for ski resorts. The possibilities are endless. Um, and then the last but not least technical conversation is the Manta. We had some hospitals and hotels in particular that said, look, we love your technology, but we just can't shut down. We're an operating hotel. I can't shut down toilets and showers for a minute, let alone an hour for you to put any hardware in. So I can't touch my sanitary, but we do have this massive hydronic loop that's cooling, large sections of the building and also heating the pool and all this stuff. And we're just evaporating all that energy to the roof. So if you can give me a heat exchanger that I can plug into that loop, I would love to explore it. So Manta was born. And long story short, if you can guarantee us that your water loop doesn't have anything in it bigger than 2.5 millimeters, we don't need that fancy basket filter. We don't need the macerator. We really just need our heat exchanger, right? With specialty piping and valve on either side and the control that looks at backflow pressure, back pressure differential, temperature, flow, and it basically will continually back flush the system to keep it cleaning itself while you're getting maximum thermal transfer. It's got clean in place ports built right into it. So this is something that sprung from hotels and hospitals, but has really launched us into data centers because those data centers have massive cooling loads. And here's an opportunity again, instead of wasting all that fresh water to cool them using evaporative cooling towers, use the Manta to harvest the energy from that data center and put it into a loop to then heat a nearby building or put into the ground and save for heating, for seasonal usage. So again, we're not just about black water. We want you to think about hydronic energy because moving energy between buildings using water or essentially non-combustible sources like water plus glycol, it's the most efficient way to do things. It really is. People are waking up finally. I was just at a New York City Economic Development Corporation info session yesterday. The city has identified that thermal energy networks are the key. They've blown right past feasibility and they said, look, we've already done the feasibility study. We want to do a thermal network at Hunts Point. using the fish market and the meat market and all that refrigeration and the nearby wastewater treatment plant. And then also at Sunset Park in Brooklyn at the Battery Army Terminal, same concept. All this great infrastructure that we can then tie together and share energy between buildings to decarbonize them in a very efficient district scale. So that's what we're using. We're going to be using the Manta and the Shark in addition to air source heat pumps, geothermal. It takes a village. There's no one silver bullet. I'm not going to sit here and tell you that this solves every problem. It solves a lot of them, but we are again very Canadian. When you connect us with other like-minded and relative or complementary hydronic assets, we get a multiplier going both ways. You get so much more out of our box, and we bring so much more out of the other box that we're connected to. Um, Again, I'd like to stop there for on the technical side. I appreciate your patience. It's a lot of information. Um, any questions on the Shark on, how we're doing thermal capture at scale before I jump into actual use cases?
Aaron, it's Bernie Pelletier. One
Yes.
question, when you're rejecting heat,
Yes, sir.
say from a data center or elsewhere, how, what's the upper limit to the temperature that you're sending out? In other words, is it scalding water? Is it going to have some adverse effect, or what's the
No, no.
range?
Yeah, so do no harm is our first rule of thumb. And we are always driven by the local municipality. So we're talking about, so when you're talking about a if you're connecting to a municipal sewer line, right? If you're doing Shark or Manta, you're dealing with a much larger flow rate. So think about a sewer that runs by your building or a wastewater treatment plant. You're getting 3 to 5 million gallons a day, right? Of that 3 to 5 million gallons, I'm only working with a portion of the flow, a very small portion of the flow. And then my heat exchanger is designed for a 10-degree delta T, meaning I'm either taking 10 degrees out or I'm putting 10 degrees in at any given moment. And I can go up to 15 or 18, but usually it's about 10 or 12
Gotcha.
degrees. So it's a fraction of a fraction. And then I'm adding a tiny little bit to this millions of gallons of water. So at the end of the day, it's inconsequential. We're happy to go through it we do it all the time. Talk to my friends in Washington, D.C. at DC Water, talk to my friends in Toronto and Vancouver and Boulder and Denver, the municipalities that are actually doing it right now. I'm working with the New York City DEP right now to on a couple of wastewater treatment plants to assess the feasibility. So, and they have been the most gun shy of all. So we're cracking that egg. It's a great question, Bernie. We're not dumping, and in fact, I would argue that in some instances, a lot of instances now, the wastewater treatment plants are under a lot of pressure to reduce the temperature of their effluent they're dumping into the local channel or the river or the lake, what have you. So by putting our machine in the tailwater of that treatment plant, right after they've done all their bugs and treatment, the water's basically clean enough to dump, but it's still warm. Let us take another 10 degrees out of that water, use it for the plant, use it for nearby property, thereby also cooling the water to make it even more um, environmentally friendly. So we're actually in a lot of cases helping out where they need to drastically reduce large industrials. I'm looking at one where they need to take 60 degrees out of the water, and instead of quenching it with fresh cold water, we're going to just circulate it through a manta, harvest as much as we can out of it to reduce the amount of energy and fresh water they have to use to cool that water. So great question. I saw a hand
Thank
go
you.
up.
I think it might have been Jeff Howard, who is almost Canadian, even though he's in. Jeff, are you still there?
Yeah, that was you hit my question, Bernie. Thank you.
Yeah. And it's something we take very seriously. And it's something that we're happy we don't shy away from it because the science will back us up. It's a great question and it's very important. It really is very important.
Right. Thank you very much.
My pleasure. So like I said, I've got a bunch of projects going on. The very end of this slide deck, I have slides that I've prepared about the program that's happening in Massachusetts. The Massachusetts DEP has launched a pilot program. And originally, I think what sparked this conversation with Peter and myself was like, hey, how do we get a program like this into Connecticut, right? And so I think it's a matter of like socializing all of the good things that come out of this Massachusetts program as it rolls out. Um, and in combination with like rolling out the good news about what's happening north of your border, it's about socializing network opportunities that are happening right now, across North America that are delivering value to not just individual buildings, because I've got great individual buildings case stories here, but district systems. One of our favorite, I mentioned it before. This is the largest wastewater project right now going on in North America. It's in Falls Creek, it's the center core of the city. It was originally designed for the 2010 Winter Olympics. There was a different technology in there that kept jamming up, so they ripped it out and put in two of our SHARC 880s. And we were at the time filtering raw sewage from a city. This is a wastewater collection center that's literally parked under this overpass in the center of the city. Just happens to be where several large gravity sewer mains and a forced main all collect before they then get pushed down to the wastewater treatment plant. So this was a natural collection point. We put two of these sharks in there, and we were providing 3.2 megawatts to provide the hot water for this center core of Vancouver, right? It was so successful that they recently ripped out these two older units. They're working perfectly fine, but they were like, hey, let's step it up. And we've now recently, about almost now 9 months ago, commissioned five SHARC 880s. We're now filtering over 6,000 gallons of raw sewage every minute. We're taking that raw sewage, that filtered sewer water, shoving it into these ginormous, not shoving, pumping it literally into these ginormous York YTK 3 megawatt heat pumps to make 180-degree hot water that we then pump around downtown Vancouver. We're now creating almost 10 megawatts of harvesting. We're not creating, we're harvesting 10 megawatts of thermal energy that we're now powering 23 million square feet of mixed indoor space in Vancouver. And it's so successful, they're already trying to figure out where they can shove a couple more units because they want to biggie size it. So, round one, phase one with these red buildings, we were basically providing, and this is 100% sewer, nothing else. Phase two, we're now powering the blue areas. They want to now pick up these additional industrial areas in the dark gray. They have the capacity. I mean, the wastewater's there. Again, million gallons a day, megawatt. They have the capacity. It's just a matter, do they have space in their plant? So here's an opportunity again where not only is it a real testament to the technology, but this is a standalone utility. What I mean by that is it is a self-sufficient utility that's selling energy into this loop. So all of the money that goes to maintaining, owning, and operating this system comes from the rate base connected to the loop. So really, really neat. In addition to us being very flexible from a technological, mechanical standpoint, we're very flexible in how we get built into the financing of projects. So here's a standalone utility. DC Water Headquarters, the utility for DC, actually they built their headquarters on top of a lift station where two-thirds of the city naturally gravity drains. So 5 million gallons of water run through the basement of this building. 5 megawatts of energy. It's only a standalone building, but perfect example of water savings. The chiller plant rejects 100% of its heat into that loop, excuse me, into the sanitary, and then we pump it downstream to the blue plains. Jeff's got another question. So what that means, it equates that they don't ever run their cooling tower, which basically equates to roughly 1.5 million gallons of freshwater savings every year. Think about it, one building, over 1 million gallons of fresh water. So now if you can do that at campus scale, it's pretty impressive to the point where the military is looking at this for water scarcity and grid hardening. Bernie, do you want to pick Jeff or Steve? This is your
Jeff,
show.
why don't you start off and then we'll go to Steve.
Yeah, Aaron,
Yes.
in the Vancouver system,
Yes, sir.
with that third phase added,
Mhm.
what fraction of the thermal resource of the sewer system would the total recovery be capturing?
The short answer is I don't know. I'd rather tell you I don't know than to know that. But if I may, that's easy. That's literally one. That's probably an email away to the gentleman who runs the plant. I can't remember off the top of my head how many millions of gallons go through a day, but it's a fraction. that third phase would still leave us a lot of extra capacity. This is a
Okay.
massive, massive, like a huge chunk of Vancouver's wastewater flows through this one plant. So
Thank you.
you're very welcome.
Uh, Before going to Steve, Aaron, it's true that the False Creek system does not do any cooling. Is that true?
Correct. Well, because again, it's only a couple of years ago, I think it was 3 years ago, when Vancouver had that heat wave and a whole bunch of people passed away because they didn't have the city up until I think 2 years ago didn't mandate cooling in buildings. It was only heating. So yeah, this is a heating only building, heating only loop. It's correct.
Steve,
Steve.
So if we were to set up a meeting with our sewer authority, like would we be looking for a map of like where there's collectors or lift stations or like where's the like ideal place to plug something like this in? Like
That's a
what are the big opportunity points we'd want to
yeah.
map out?
It's a great question. So natural collection points, pump houses, lift stations, wastewater treatment plants. Those are obvious um, locations because there's usually a wet well already in place. There's usually a battery, if you will, right, already in place. Anytime we can use existing infrastructure, so much better just for civil costs, for permitting, for everything. It's just easier. Again, Washington, D.C. Water is actually actively courting building owners to tap into the sewer in front of their building. So that's a little bit that's a bigger lift, heavier lift, and they've been at it for a little bit more time. And I'm happy to dive into that about what their efforts are down there. But to answer your question, the easy winners are when you can get that natural collection spot. Again, lift station, pump house, wastewater treatment plant, and then ideally one of those assets is nearby an off-taker. Because as I mentioned before, in an ideal world, your wastewater source, your tank, and your SHARC plant are really close to each other because we're
Right.
trying to move the wastewater around as little as possible, right? So ideally they're all kind of here. In an ideal world, your apartment complex or your hospital or your prison, whatever it is, like that we're trying to is right nearby. So all we have to do is essentially horizontally bore over, right, to connect that building to send that condenser water into the building. That's really what you're looking for. I'm looking for a rich energy source, natural collection point, and on one side of the equation, and on the other side of the equation, a load profile that matches this, right? And hopefully they're nearby each other. We don't have to cross any train tracks. That's a nightmare. You know,
I'm going to ask a question also,
please.
Aaron. So you know that one of the big issues for ambient temperature loops is the issue of providing maybe 130-degree water to existing buildings that were used to getting 180-degree water. That expense is a challenge. Now, I heard you refer to a system that was using an unusual heat pump that could boost to 180-degree water. Are those
Yes.
are those heat pumps so unusual and so expensive that they're not going to pencil out for most projects, or is that becoming into the realm of possibility?
Well, that's a great question. Those YTK heat pumps, they're massive. Imagine like a ginormous, natural gas boiler for a huge commercial building, right? We're talking that size. So that's more of a municipal district level heat pump. There are companies, and you're spot on. Like you're this is not just a problem for us. It's just electrification in general, building modernization in general. It's hard because a lot of these buildings I'm just north of Manhattan. So many Con Ed steam buildings or buildings that are built for internal steam to convert them over to hydronics it's a fool's errand because it'll never pencil. However, there are companies like Oilon, Oilon, happy to connect you with them, lovely people, Finnish company. My friends at MPN Boilers in New York represent them. They have a heat pump that can make steam. They can make, I think, low and mid pressure steam up. I forgot the exact number, but like two. I'm not gonna. I don't want to say it wrong, but Oilon is a heat pump manufacturer that can make steam for a building. So we're exploring projects with them for these Con Ed buildings where rip out that old dual fuel natural gas steam boiler, put in a SHARC, right, to capture the sanitary leaving the building, use that to make the condenser water to then feed into this oil-on heat pump to make steam to then feed into the steam loop. So you don't have to redo the whole internal building. So that's one way to go about it. Uh, there are some buildings that are just not good candidates for full electrification, which is why you do what you can. To me, progressive means pragmatic. Hybridize it. Just electrify what you can and just keep moving on. So,
Uh,
Mark,
Mark.
Hey, Aaron. I'm a Canadian from Vancouver. Um, how did you know how Metro Vancouver Sewerage Authority or Water Authority has the rights to Falls Creek? How does one carve out a system like yours? Is there a high level political work you do with the utility, or how did they manage to do that? Do you know?
yeah, that's an impressive question that we can talk about. I referenced that NYC Economic Development Corporation meeting I was at yesterday. That's the hard shot, man. Especially when you're dealing with these large district systems, you've got multiple stakeholders. You've got the municipality, got the utility involved, private ownership. There's right of way permitting. It does take some political push. So it takes a village and it takes everybody kind of pulling in the same direction, which is why these thermal networks have not really taken off because it's really hard to do in the United States. It just really is. First of all, the profit motive, is one challenge, but then all of these again, permitting and environmental concerns, what have you. In some, I've reading this great book, Abundance by Ezra Klein, and I forgot his co-author's name. Great book if you want to dig into it. But in it, he talks about how, you know, environmentalists have essentially spent decades perfecting the way of stopping things from getting built, right? Because it's going to hurt this owl or this watershed. We need to figure out a way to be progressive, to be modernizing, but build things. We have to build things. We have to be thinking positive forward. So great question. Happy to talk to you offline. Happy to loop in some of the people that were certainly more involved than I was. Because again, I'm in New York, and that Falls Creek project's been in operation now for years. So it predates my time at SHARC, but Lynn Mueller and Hans Paul Panu, the guys who've been there from the beginning. I'm happy to loop up with any municipality that wants to kind of talk about all of the lifts that are taking place. I mean, listen, I was talking to Peter about this before the webinar started. We have a New York State lobbyist on retainer because we have to work the legislature, right? We're working hand in glove with the pipe trades. The UA, the steam fitters and the plumbers have been amazing for us because there's a workforce development aspect of this. We're putting a Piranha into every local training center across the state because we want men and women to get in there, young apprentices to learn how to install, maintain, replace, fix these machines. And the state is really behind it. There's $150 million for thermal just for energy in general in New York State, and it last budget round was like 400 million with 150 specifically for thermal energy networks, and that's all because of political pressure from the pipe trades, from a workforce development aspect, from now it's really from we need to get the engineers of record and the developers on board. Because when the moneyed interests and the people who serve them, i.e. the engineers who are really putting these things on paper, once they join the team, all of those conversations that sound really challenging become a lot clearer because you've got now money behind it. Jeff.
Could I just
Please.
interrupt for a minute?
Of course.
Aaron, I'd like you to go through a few more of the case studies before we
Sure.
go to questions.
Yeah. So
my apologies to Jeff, and I would imagine that we can go over a little bit.
yeah, and I've got time for you. Happy to do it. Ambient temp. This is Vancouver. This is a great district system. By the way, anybody who wants to go visit DC Water, let me know. Happy to set up a tour. Happy to take you to some sites in Brooklyn, which are up and running. Also, if you can get yourself out to Vancouver within like a couple hours in any direction of our factory, I can take you to like a dozen really cool projects, everything from a multifamily residential building all the way up to Falls Creek. And this is one of the projects, Lelum, which is a new construction village, mixed use village, that is basically powered pretty much 100% by sewer. This is our baby shark, our Shark 660. As you can see, we're capturing, excuse me, just by using the gravity sewers coming out of the buildings on the campus, as well as a city force main that runs through the campus. We're able to side stream enough wastewater to put it into these batteries, right? And interestingly enough, these are two 10,000 gallon batteries, wastewater holding tanks. We're only using one of them right now. This is new construction. So one of the great things about this project is they were able to plan for future development, which is why you've got all this extra space in this the central plant and the additional tank, so that when they need that additional capacity, all they have to do is valve it open, and now the battery is doubles in size. So what I wanted to talk about Glelum is, because it's new construction, it was really inexpensive to lay the HDPE, the pipe in the ground, and to put the shark in to connect the buildings. So there's a passive loop, this red line that runs around the campus, and all the buildings are connected to it, right? That loop stays at 66 to 80 degrees throughout the year. And everybody on the loop pays a flat $20 fee. Everybody has their own electricity bill. So if you're the supermarket, you obviously pay more than Mrs. Schwartz in the apartment over in this building, right? But Mrs. Schwartz and the supermarket both pay $20 into the loop fee. $4 goes to paying to keep the loop and the shark maintained. The other 16 is going into a revolving green fund that are going to pay for phases 2 and 3. So not only did this pay back in like 100 months, and I never talk about payback with electrification because it never pays back that fast, or rarely does. But here's an application where, because it pays so well, not only is it paid back, it's paying forward for future development. So here's a great argument. This is when you can start putting this in front of developers, they start to see the value. You can start bringing this in front of a college campus, and you can start thinking about how you can bring value to an ongoing operation. And this is a district center. It's a little unique in the sense that this is northern climate, not allowed to say who it is or where it is, but a northern climate First Nation is being courted by a hyperscaler to put a data center on their land. And because these First Nations have a mandate to look 7 generations into the future to do good, they are trying to reimagine these data centers as a thermal hub, an energy hub. So now what they're doing is they're taking the captured energy from the data center, putting it into an ambient temperature loop to run it around to not only you can read this, heat the pool. They're going to do snow melt. There's actually a nearby community that they're just going to give free heat to, because they can and they want to. So again, repurposing existing assets, especially data centers, are getting a terrible name right now, rightly so to a certain extent, about being energy hogs and water hogs. Well, now think about it. If you can get on-site power generation with solar, small modular nuclear reactor, quite frankly, anything, you've eliminated the bring your own power problem, and now you just have to deal with the water conservation. And water conservation is a huge, huge selling point, because depending on the municipality, there's a lot of, you pay money for the evaporative, the cooling, the blowdown and all that going out, and then also your sewer charges. So if I can, in one fell swoop, reduce your sewer charges and reduce the amount of water you use for your cooling tower blowdown and all that, massive savings on top of the decarb savings, on top of all those other benefits. And now you can start essentially, and this is what I'm doing. And I'm as progressive as the next guy. I don't talk about environmental concerns anymore. I talk about money. I talk about the fact that these systems can drive CapEx savings, OpEx savings, water savings, risk aversion. You can also, with you've got resiliency with grid hardening if you have on-site power generation. Those are selling points to moneyed interests. They just happen to get all these great environmental benefits that fall off the turnip truck, but I don't ever have to bring them up anymore unless there's an ESG goal behind it. Some people still care, but a lot of the developers I'm working with, especially in the greater New York area, that sounds great, and they do like to virtue signal, but it really comes down to pencil. If it doesn't pencil, it won't get built. Any Peter, any questions? I mean, I've got some more conversation, but we didn't even really touch on what's happening here with Massachusetts. I'll leave this up and let you guys read through it. essentially Massachusetts got wise and caught on to what New York State has been doing. And give them some credit for some independent invention, but New York State has had a PON out, a public offering notice, for a while now, where they have categories 1, 2, and 3, where they will fund feasibility studies, design drawings, and then implementation of projects that they deem meaningful. And so what Massachusetts has done is kind of followed suit, and they've come up with a three-tiered pilot project for wastewater. They're calling it energy recovery, but wastewater heat transfer, as we energy transfer, as we call it. And basically, as you can see, who can apply? Anybody can apply. If it really comes down to it, what they're looking for is they're really looking to deploy these ideally in disadvantaged communities. They really want to look at cross-market sectors. So we're looking at multifamily residential, wastewater treatment plant, light industrial, commercial, what have you. And they've broken the program, much like New York State, because it just works into 3 tiers. And again, I'm just going to let you guys read this stuff because it doesn't make any sense for me to read it to you. They want actionable projects. It's great. They really have put an eye towards projects that are going to develop real coalitions and deliver real value, not only from an energy standpoint, from an energy equity and affordability standpoint. They're really taking the right approach, in my estimation, on the project. So $5 million total pool. They think it's going to be about 8 to 10 because again, these aren't hard numbers as far as like what's being allocated and what the project's going to cost, but they think doing the math that with $5 million pool, which is a small one to start, they can do about 8 to 10 projects. First come, first serve, rolling basis is actually open now. I'm in the process of submitting some projects right now. We're going to be doing a low-income multifamily residential building using a Piranha. And then we're looking at a couple of large wastewater treatment plants with the SHARC or Manta to do more of a district or large scale system. So we're trying to provide them again with cross market sectors, cross disciplines, applications, scale, what have you. So as you can see here, phase one, it's not a lot of money, but it's something. And the good news is we're finding that there's such a cache of small energy firms in Massachusetts in particular because of these technical assistance programs they have through Eversource and National Grid, that there's a cottage industry of small energy firms that can do a feasibility study for 15 grand, no problem, right? It's basically an ASHRAE level 1 energy audit. The state will determine which ones they deem viable. They'll award them 15 grand for a feasibility study. And then, by the way, if you already have your feasibility study done and you want to go right to phase two, they'll take it and run with it. But the ones that they deem worthy of the feasibility study will then be able to submit their feasibility study and say, hey, look, we think we got a project here. If the state agrees, they'll give them up to, as you can see, 100 grand to do design drawings to be able to take that drawing set to street to get a bid, a range of magnitude bid from a contractor. And then, as you can see here, there'll be implementation money at the end. And they'd like to see, I think, at least 3 or 4 really good projects come to fruition. And it's all based on a scoring rubric. And again, this is all public knowledge. I just grabbed some key slides. If you just Google Massachusetts DEP wastewater pilot, the whole thing will come down. I didn't want to bore you with all of it, but like I said, they've really come up with a straightforward rubric on how they can score the quality of the projects. And as you can see here, they've put great concern into a lot of different aspects. It's not just about the dollars and cents. It really is about the I can't speak, real world value, especially to energy communities that they can deliver. And then this is just some last little notes here. I'd love to help you guys, help the state of Connecticut. When I say you guys, gals and guys, bring this to Connecticut. This is happening over the next couple of years, so it's going to be some time before tangible results come out. But the good news is I've got I've got projects and success stories that I can share from not only New York State, but around the country. And the good news is geothermal and wastewater energy transfer, thermal storage projects, they're still federally incentivized through the ITC. So because I think we're close enough to geothermal, oil and gas, somehow this technology has survived the wind and solar debacle that the Trump administration has affected. But so there's good state level incentives, utility level incentives, and federal level incentives that are generally available. And I'd love to help you figure out the matrix of stakeholders and financial entities in Connecticut that can help get these pulled across the finish line, either through public-private partnerships, ESCO-driven models, privately owned models, or just straight up utility municipal owned models as well. They're all very viable.
Well, Aaron, thank you so much. That was a lot of information, a lot of insight, a lot for us to chew on. Um, at the risk of going way over, if you have some time, Aaron, and there are some questions, we
Sure.
can go on for another few minutes or more.
Yeah, let me look. I've got a half hour. So if you guys have questions, that means I didn't put everyone to sleep, which is a good sign.
Bernie,
Aaron, no, you have not put us to sleep at all. I think the wheels are turning here, or maybe the auger in
There you
like
go.
the
Well
shop.
done. Well played.
One very specific question. We have here in Connecticut, it's a consortium of our two utilities, and they run the efficiency programs.
Hmm.
One of those programs is RNC, Residential New Construction, where it really should be electric new construction. So they give incentives and guidance.
Hmm.
And domestic hot water is one of the hardest things to do in a residential new construction environment to get that done with heat pumps.
Interesting.
So, would it be fair to characterize what you've told us today as, I think it is not the shark, it is not the
So the
manta.
piranha, and that's why I pulled this slide up.
Yeah,
So
it's the piranha.
but you can use, so I have in Brooklyn right now, literally face to face, two buildings. One building has two piranhas in it, providing 100% of the hot water for the building. Across the street, a much larger building with like 500 some odd residents, there's enough wastewater coming out and enough of a load profile going in that we have a shark in it. And so, whereas the piranha makes the domestic hot water directly, right? The shark across the street is making the energy for the process loop that then runs into a Colmac, in this case, heat pump, right? To make the hot water. So we're providing that condenser water for the heat pumps that do the heating, cooling, and hot water production for the building. So again, we can support direct hot water production or indirect in a
Perfect,
multifamily residential building, and we've got it proven all over the place. So it's
perfect.
yeah.
That's
And again, rule of thumb, you put that piranha in, and just if you can capture all the wastewater before it leaves the building, like that final black pipe, um, the piranha can make 91% of the hot water for the building.
uh, and I see in your slide that it says from 35 to 350 units. So 35 is pretty small. Do they all have to be in the same building? In other words, could you have five, I don't know, 5, 10 unit buildings that are close together? Can
I
you
would,
loop them together?
in theory, yes, but I kind of going back to this theory, I don't think that that's going to pencil. So our small, and I put 35 down there. I'll be honest with you, like again, 50 units is usually there's like definitely enough people in it to make it work. I have a 37 unit apartment building in Boulder, Colorado operating right now, but it's a special situation. It's like kind of like Boulder, Colorado's Silicon Valley. So if you want to develop there, you have to be completely passive house net zero ready. So this building is like beyond, it's got vertical, horizontal solar, every single bell and whistle you could think of. So that's why, and they have a mandate for like fully electrified hot water production, which is why it works well in that building. I'm not going to tell you that that same building in the middle of Hartford is going to pencil, right? So, so it's a case by case basis. So the bigger the building, the easier it is for it to pay back because again, you're getting that trade-off.
Dan.
Yeah, thanks, Aaron.
My pleasure.
What's the life expectancy on a SHARC unit?
So we build them for a 25-year lifespan, just like you would a standard boiler. Again, they've only been operational for 16 years, but so far so good. Usually, you're going to have to replace the lift pump, right? That's feeding the system before you actually have to replace any of the hard components inside of a SHARC. Because again, the SHARC is really a wide gap plate and frame heat exchanger, which was designed for ethanol and citrus production. So really robust industrial grade heat exchanger. You've got some piping and valving, and then a stainless steel basket, right? The auger and motor, there's a moving part that you're going to have to probably replace. The cutting stack on the macerator will have to be adjusted and replaced in, let's say, 5 or 6 years. So there are small components that you cut, just like a car, right? That you replace over time that you can then keep the machine. But we're built for a 25-year lifespan.
We have a wastewater treatment plant that is near but not adjacent to a multifamily housing project.
Mm-hmm.
What's the magic distance?
It all depends on what we're trying to cross. If it's one owner butted up against another owner and just a pipe crossing one property line, great. If you've got the wastewater treatment plant and then 5 owners and then there's development,
No.
and I got to talk to those 5 people.
No. Just the physics of it, not the
So
property ownership.
there really is no magic number because I'll tell you, there's a project that I can't speak about because it's really, really secret, but there was so much wastewater available and the payoff at the other end was so powerful or so monetarily significant that it made sense for them to literally trench a quarter of a mile this pipe to get the condenser water over there because it just made sense. I've seen some projects where, if you have to cross one thoroughfare in New York City, it probably costs more than trenching a quarter of a mile in this place in the middle of nowhere, right? So I hate to say it depends, but there is no magic number. It really depends. But happy to help you explore it. The good news is we've got really, really good engineering partners that we can bring to the table to help answer these questions.
Great, thanks.
My pleasure.
So, Aaron, there's a question from Catherine. Would any municipal facilities, I'm not sure I can see the whole thing, be good for this on their own, like an indoor pool, ice rink, schools,
Sure.
community centers, libraries, or would we be looking at partnering with our waste or sewer utility?
Great question, and the answer is both. I had pared this down. I actually have a slide that I made for the UBS arena where the Islanders play hockey. Hockey arenas are great, especially if you've got any kind of amenities. We just did it's built, it's being commissioned right now. A community center out in Wisconsin. We're using sanitary from the kitchen and the toilets and the showers and the pool, what have you, to make hot water for the community center, and they're going to use that hot water for potable purposes and also just to heat the pool, right? So a whole bunch of different cool things. So the answer is yes. We have a very rudimentary intake form. I mean, it literally couldn't be simpler. Tell me about your building, which is again that magic equation. On one side, tell me how much hot water I have or how much wastewater I have. If it's a multifamily residential building, give me the occupancy, right? If you don't know how many people, tell me the stack. Three bedrooms, 2 bedrooms, 1 bedrooms, and I can use ASHRAE assumptions to figure out how much wastewater we think is going to come out, and then what that hot water load profile is going to be. If it's a community center, tell me about the community center. Hey, I've got 2 commercial kitchens, I've got 6 showers, 10 toilets, this many sinks. Like your typical plumbing schedule. If I have that information, we can backfill it and kind of get an understanding, and then pretty quickly give you a sophisticated back of napkin analysis that says not only like, hey, we think it's going to work. Here's the complement of hardware we recommend. And then here's all the other things you're going to need to plug into your energy model. We need you to have this much wastewater storage, your battery, this much domestic hot water storage, if it's that kind of play. Here's your kWh increase because it's an electrician, right? We're adding electricity to the load. Here's your GHG offset. your comparison to the local grid, because the EPA makes that available. So you can then go take that, plug it into your model to see if and with your utilities and see if it makes sense. If we're saving you this many MMBTU, what you're paying per therm on that versus your electricity costs, and away we go. So sorry, it's a long-winded answer, but yeah, we've looked at municipal standalone buildings. If you have a big enough admin building in your wastewater treatment plant, we've got Seashell, I think, out in Western Canada, where the plant's just the right size, where we're using the heat that we capture just to heat the building that it's in, and it made sense. So again, standalone buildings, network buildings, partnered. We've seen it all, and they all work.
So unless somebody else has another question, I have a question, which is that it's easy to understand how wastewater, with its higher temperature than ground ambient loops, would be great for heating buildings. There's just a lot more heat to pull out of that water,
Right.
of that liquid. As a thermal sink, the wastewater loop seems like it would be harder to dump heat into that than into a geothermal ambient loop. What am I getting wrong there?
No, I mean it's not any harder. I would say that one of arguably the hardest part about geothermal, short of the cost, right, and the complexity of getting it installed, is the balancing. If you're working with a really good geo company, a Salis, a CDM Smith, the Jacobs, or one of the other Gray Edge Group, I can name a host of really good geo designers. That dispatch model you can hang your hat on, and you're going to get good balancing throughout the year. I find that a lot of geosystems are just being operated incorrectly, or just being hammered, or just like so. I find wastewater to be far easier actually to balance. It just comes down to, are you combining those two systems, right? Is it a question of geothermal plus wet, or is it an either or, right? When they're working together, I think it again, if you go about it, if you approach it, excuse me, from the beginning with the right mindset as far as balancing the loop and understanding how much you can take out of or put into the wastewater throughout the year, you get that balance right. And I actually think it makes the whole process simpler. But there's a le- I'm saying there's a level of complication initially to understand the concept, but once you have it down, that's what I'm saying. Like, that's why it's so important to get the right engineering partner, right? That's why it's so important to get the right plumbing contractor to install our system, because I've seen beautifully designed systems, and then I go look at it and I'm like, okay, that pipe is backgraded. There's no way it's going to drain that way. So it kind of takes a village. You got to build everything properly. But Peter, I think that what you raise, the meta question inside your question is actually more important, in the sense of just like demystifying the complexity. And it feels like it's more complicated than it really is, but it just comes down to good science.
Okay. Um, well, we're past 1:45. I'm going to ask one last question, which is that what I'm taking away from this is that for an existing building, whether it's let's say it's a multifamily and it's big enough, it's more than 50 units, say,
Sure.
so it's an existing building. Um, it's probably pretty easy and probably financially feasible, pensable to install a Piranha and take care of domestic hot water issues. Um, Now, and that's a lot easier, say, than doing the heating and cooling because of the issue of the different temperature water that the system may be used to getting versus what it will get out of a, a heat pump system. Am I mangling that, or am I getting it right?
No, well, I think, well, the Piranha system is simpler in that we're just dealing with one system, whereas the SHARC, you're connecting to a process loop when you have other heat pumps. So it's a more sophisticated, larger system that requires more controls, right? Because you're operating a lot more machinery. But when you get down to it, it's less about that. And if you're talking about retrofitting a building, right?
Yep.
That's always the hardest part. We've got a four-letter acronym, WASH, which is ironic for a wastewater company. But if you take me to any of your existing buildings, within 10 minutes or so, I can just look at four criteria and determine if it's a good fit. W, where's your waistline? Right? We were talking about before that single black pipe. Can I get access to that pipe easily? And can I tap into it in such a way where I don't negatively impact the gravitational outflow of the building, right? Do no harm. And can I install my battery nearby that pipe in such a fashion where, again, it just makes sense? That's W. Where's your waistline? Can I get access to it? A, ample electrical capacity. A lot of pre-war buildings don't have enough juice to handle all the heat pumps. So if you've ever, I don't, if you've never tried to bring Con Ed service to a building, don't. It's awful, and it takes 3 years, and it's so expensive. So if you don't have enough juice, you're not gonna be able to run this system. S is the big one, space. Do you have room for the piranha, the shark, the tank, the pipes, the pumps, clearance for service? Can I get from the street down? All that stuff, right? That's the big one for retrofits, because oftentimes, especially down here, I'm trying to fit this much equipment into a space this big. And then H is where's your hot water plant or the thing that I'm connecting to. Because again, in that ideal world, the pipe, my tank, and my piranha are right next to each other. But if the hot water plant is on the 17th floor in a penthouse, right, it may not be feasible to make the hot water in the basement and pipe it up there. But if your hot water plant happens to be right in the next room, or if the building is, I've looked into some buildings in Boston where 6 story, 7 story building, sanitary leaves the parking deck, and there's a drop ceiling in the parking deck with a chase up to the roof, and the stuff's up on it's like, wow, this is perfect, right? Make your hot water, store it in the parking garage, and then just pump it up. So that four-letter acronym pretty quickly can tell us if we've got a shot. And then the unspoken letter is C, the customer. Because I've been into some amazing buildings in New York City that are tailor-made for our tech, but it's a co-op. And they can't agree on the color of the mailbox in the lobby, let alone can I put 5,000 gallons of wastewater in your basement, sir? So sometimes just avert your eyes and back away slowly. But no, but in all seriousness, that's really the trick. Retrofits are tough. Retrofitting a like-for-like boiler replacement is hard, right? But they need to be done. New construction's much easier for us because you can be considered as part of the base building system, but much longer development cycle, and you have to be in really early because ideally we're probably trying to pour a tank into the foundation, right? We're trying to like be part of the heating, cooling, hot water production. You can't design all that and then as an afterthought throw our stuff in on it, right? So a lot of coordination, kind of going back to, I forgot who asked that great question, our friend from Vancouver, about the interconnected stakeholders and just the varying interests and where they're all pulling in their own different direction. So, but we're getting it done, and I'm excited to do it with you guys in Connecticut. So let's find some projects. I can distribute that intake form. Happy to do free work for you. We are notoriously good at doing free work for people. So if you submit some intake forms, we will turn around some really cool, essentially graduate level book reports about your building. So it'll be my pleasure to do so. This has been a lot of fun.
Great. Thank you so much, Aaron. We've taken enough of your time and really appreciate it. As I said
I
before,
love this. If you can't tell, I never thought my wife hates when I say this, but like 54 years on this planet, and I finally found my niche, and it's the sewers. So, you know, I love this. So you're never bothering me. If anybody wants to do a deeper dive, give me a call, send me an email. Happy to take time out, do lunch and learns all the time. Although wastewater and lunch and learns, it's a little touch and go sometimes.
right, right, but I think we could do it. So,
Happy to do it.
and I'll just end by saying, remember, no meeting, webinar, anything in July and August. We'll see you in September. And thanks, and have a great afternoon.